Welcome to the lecture on solving linear equations. Let's start by defining what a linear equation is. A linear equation is any equation that can be written in the form ax plus b equals to c, where a doesn't equal 0. So you need to have an x to the first power in your equation. For example, something like 2x plus 3 equals to 5 would be an example of a very simple linear equation. Non-linear equations are much more difficult to solve. How would you recognize when you have a non-linear equation? Well, it would contain terms like x squareds, x cubes, x to the fourths, any higher power of x, square root of x, absolute value of x, or even fractions where the x is in the denominator. So if you see any of these types of terms, then it's a non-linear equation and it's going to be a little bit more difficult to solve. Now, when we're working with the linear equations, there's three situations that could occur when you find your solutions. There might only be one solution to your equation, and that's the most common case, and that's called a conditional equation. An example would be x plus 3 equals 5. We know that that's only true when x is 2, so that's the only value that works, so you only get one solution, 2. Sometimes when you solve linear equations, you get no solution, which is called a contradiction. An example of this might be x plus 2 equals x. We know that that's always false because there's no way you can start with a number, add 2 to it, and get back the original number. So that has no solutions when we try to solve it. How do you write your answer? You either write it in words, no solution, or you can use this notation 0 with a slash through it. The third case when you solve a linear equation is you might get an infinite number of solutions, and this is called an identity equation. An example of this would be 2 plus x equals x plus 2. We know that that's always true because addition is commutative. So 2 plus x, when you switch the order around, equals x plus 2. That's going to be true no matter what value of x we use. So what do you write for your solution? We write it in words, and we write x equals all real numbers. So to summarize, these are your three cases. When you solve a linear equation, either it's an identity, which means it's always true, and your solutions would be all real numbers, or you have a conditional equation, which is true for only some values of x, so your solution would be x equals a number, like x equals 2 or x equals 5. The third case is you have a contradiction. This is going to occur when you have an equation that's always false, and your solution to that equation would be no solution. Either write it with words or write 0 with a slash through it. Now, when we're trying to solve linear equations, our goal is to get x by itself and isolate it so that we can get x equals a number. So we're going to get x's on one side, all the numbers on the other side. There's several steps to follow when you're solving a linear equation, and here's a list of what you can do. Step 1, I call this the cleanup stage. In this step, what we're trying to do is make our equation easier to work with, so we clear out fractions, clear out decimals, and clear out groupings. And by groupings, I mean any kind of parentheses, brackets, any kind of grouping symbol. And also, if you have any like terms on the left side or the right side of your equation, you want to clean that up as well. When we clear out fractions or decimals, we're going to basically be multiplying both sides of our equation by the lowest common denominator. And when we clear out parentheses, we're going to be using the distributive property. So step 1 is cleaning up your equation and getting it as simplified as possible. Step 2, once it's cleaned up, then you're going to get your variables on one side, and you're going to get your constants on the other side. And we do this by adding or subtracting terms to both sides. You want to make sure you do it to both sides of the equation to keep the equation balanced. Step 3. Make the coefficient of the variable term a 1. So once you have your x term on one side, sometimes there's a coefficient in front of that x. So to get rid of that coefficient, we're just going to divide both sides by that coefficient, and we'll have our x isolated. So at this point, you should be finished. You want to make sure that your answer is in simplest form, And if you have time, you can always check your solution by plugging it back into the original problem. So let's start with an example. 4x minus 3 minus 8x plus 1 equals negative 5x plus 9. Now in this example there's no fractions, there's no decimals, there's no parentheses. However, there are like terms on the left side of the equation. So first thing we want to do, clean that up, simplify it. So 4x minus 8x is negative 4x, and negative 3 plus 1 is negative 2. So we're just cleaning up that left-hand side. Now we're ready to move on to step 2, which is to get your x's on one side and your numbers on the other side. Remember that it really doesn't matter which side you move your x's towards. Once you do that, that's going to determine which side your numbers go towards. What I like to do is try to make that coefficient in front of the x as positive as possible. So if I can avoid any negatives, all the better. So in this example, I could add 4x to both sides, or I could add 5x to both sides. I'm going to choose to add 5x to both sides, because if I do that, then negative 4x plus 5x becomes a positive 1x. So make sure again that you're doing it to both sides of your equations. This is now our positive 1x. The minus 2 comes down. This cancels out to 0, and our positive 9 is still left over. So we've moved our x's to the left side. That means we need to move our numbers to the right side. So to undo subtraction by 2, I'm going to add 2 to both sides. These will cancel out, giving me just my x, and 9 plus 2 is 11. So I have x totally isolated, there's no coefficient in front of it, so I'm finished. X equals 11. Okay, next example. On this example, we do have some parentheses, so we're going to start by removing the parentheses using that distributive property. Now the first set of parentheses actually doesn't have anything in front of it to distribute, so these first set of parentheses aren't even necessary, so I'm just going to go ahead and drop them. However, the second set of parentheses are necessary because there's a negative in front which I need to distribute across. It's like a negative 1 being multiplied by my two terms. So negative times 7r is negative 7r, and negative times a positive 1 becomes minus 1 equals our negative 6. So we've eliminated our parentheses. However, on the left side we still have some like terms, so you want to get those combined first before you start moving terms to the other side. So 8r minus 7r is 1r, or just r. We don't have to write the 1 in front. Negative 3 minus 1 is negative 4. And now we have our r totally by itself on the left side, except for this subtraction by 4, so I'm going to have to add 4 to both sides to undo that. And now we get r by itself. Negative 6 plus 4 is negative 2, and we have r solved for. So r equals negative 2. Next example, more parentheses, a little bit more distributing involved. So first step, distribute any coefficients out front of those parentheses. So 9 times 2m is 18m. 9 times minus 3 is minus 27. On this second set of parentheses, you want to be really careful. One common mistake that students really make quite often is forgetting to distribute any negatives. And in this case, we don't want to distribute just the 4. We want to distribute the negative with it. So negative 4 times 5 is negative 20. Negative 4 times positive 3m becomes negative 12m. On the right side, distributing the 5 times 4 is 20, plus 5 times n. And then the minus 3 just carries down. So we've eliminated our parentheses. Now we want to combine any like terms on the left side and combine any like terms on the right side before we start adding or subtracting things to both sides. So on the left side, 18m minus 12m is 6m. Negative 27 minus 20 is negative 47. On the right side, 20 minus 3 is 17, and that 5m just stays put. Now I'm ready to get my m's together. I usually move the variables first, but it really doesn't matter whether you move the numbers or the variables first. To keep my coefficient in front of m as positive as I can, I'm going to choose to subtract 5m from both sides. That way 6m minus 5m becomes a positive 1m. These cancel out to that m. The minus 47 is still there. The 17 is still there. And these cancel out to 0. Now that we have m by itself on the left side, we need to add 47 to the right side to further isolate m, and we get m equals 17 plus 47, which is 64. So our solution is m equals 64. Now remember, in all of the examples that we've just done, we've always gotten one solution only, m equals 64, for example. And these are called conditional equations because they only had one solution. On the next couple of solutions, we're going to see those other two special cases. So for example, on this example here, we have parentheses, so I want to start by distributing. And when I distribute, I'm going to distribute the negative with the 4. So the 6x will stay put. Negative 4 times x is negative 4x. Negative 4 times positive 2 is negative 8. This minus 2 carries down, and we still have our 0. Now when we go to combine like terms on the left-hand side, 6x minus 4x is positive 2x. Positive 2x minus 2x cancels out. So in this example, all of these x terms cancel each other out. So there's no x left. Whenever that happens, whenever your x's disappear, that's always going to result in one of those other two special cases, either an identity equation, which is always true, or a contradiction equation, which is never true. The way that you tell which case it is by looking at what's left over. If all these x's are gone, I still have a negative 8 on the left side, and I still have a 0 on the right side. Does negative 8 equal to 0? No. So that's a false statement. And if you have an equation that's always false, like this one, that, remember, is called a contradiction. Now that's just the kind of equation it is. It's not going to be what we write down for our solution. When you write your final solution, remember that since a contradiction is always false, there's no value of x that's ever going to make it true. So our solution is no solution. You can either write 0 with a slash through it, or you can write it with words. Okay? Alright, let's try another one like that. So on the next example, again distributing first to get rid of parentheses, this would become 3 times 6, which is 18, and 3 times minus 4x is negative 12x. On the right side, 2 times negative 6x is negative 12x, 2 times 9 is 18. Now I have x's on both sides, so when I go to get them together on the same side of the equation, I might add 12x to both sides. But look what happens. They cancel out on both sides. They zero out on both sides. So again, when your x's disappear, you are going to have one of two possibilities. Either an equation that's always true, or an equation that is never true. And how you tell the difference is by looking at what is left over in the problem. In this problem, I still have 18 on the left side. I still have 18 on the right side. Does 18 equal 18? Yes. So this is always true. And if an equation is always true no matter what x is, that was called an identity equation. Okay? Now that's not what you write for your solution. When you're writing out your actual answer, remember that if an equation is always true, that means no matter what x I pick, it's always going to make the equation true. So every value of x works. So the way we write that is x can be all real numbers. So write it out with words. So your solution, all real numbers. Okay, so to summarize here, if when you're solving an equation and your variables cancel out and disappear, then you will either be left with a true statement, like 0 equals 0, or a false statement, like 0 equals to 1. If you have a true statement, then your solution is going to be all real numbers. If you end up with a false statement, your solution is going to be no solution. So look out for those special cases when your variables disappear. Alright, now we're going to move on to a little bit more complicated examples, some examples with fractions and decimals in them. In this first example, we have some fractions, and what we often will do to make our life easier is try to clear out the fractions first before we start moving terms from one side to the other side. And the easiest way to clear out a fraction is to look at all your denominators. In this case, the denominators that I have are 5s. We want to use our least common denominator, which in this example has to be 5, since that's the only denominator we have. And what we're going to do is multiply the entire equation by 5 on the left side and by 5 on the right side. You must do it to both sides of the equation, otherwise the equation won't be balanced and you'll get a different solution than what you should be getting. So when we multiply the left side by 5, 5 times 1/5, well, when you take 5 times 1/5, this 5 in the denominator cancels with the 5 in the numerator, and all we will have left is 1 times x, which is just x. Then I'm going to bring down my subtraction. When I take that 5 times the 7, 5 times 7 is 35. Remember, we have to do 5 times every single term in the original equation to keep it balanced. On the right-hand side, when I do 5 times -4/5, the 5 in the denominator cancels with the 5 that we're multiplying by, so all we're going to have left is the -4 and the x. And then the last thing we need to do is multiply the 5 times the 7x. 7 times 5 is 35, so this will be 35x. Now, before I start moving things from one side to the other, we do have two like terms on the right side, so let's clean that up. We have x minus 35 on the left. -4x plus 35x is 31x. Now, since I already have this x term by itself on the right side, let's take this x and join it with it. So we're going to subtract x from both sides. That way, these two x's will zero out. I still have the -35 on the left side, and 31x minus x is 30x. Now, in this problem, I do have a coefficient in front of my x. So to finish isolating it x and getting it by itself, I'm going to want to undo that multiplication by 30, and I undo it by dividing. So these will cancel out, giving me x by itself. And right now I have -35 over 30 as my solution. That would be an incorrect final solution because that fraction isn't reduced. Since both numbers end in either 5s or 0s, we know that that is divisible by 5. So let's go ahead and divide the top by 5. -35 divided by 5 is -7, and 30 divided by 5 is 6. So the reduced solution would be x equals -7/6. Okay, let's go ahead and move on to this next example, which has a lot of fractions in it. So when we look at this, our first goal is to try and clear out all those fractions, all those denominators. And in order to do that most efficiently, we're going to try to find out what the least common denominator is. So look at the denominators that we have to begin with. We have 3, 4, 8, 9, and 6. So what we're looking for is a number that 3 divides into, 4 divides into, 8 divides into, 9 divides into, and 6 divides into. So when I'm trying to figure out a least common denominator, what I often do is take my two largest denominators that I have, in this case 8 and 9, and think about what the common denominator might be for just those two numbers. So 8 is 2 times 2 times 2, 9 is 3 times 3. There's no overlap in those factors. So the only way to get a common denominator for 8 and 9 is to multiply the 8 times the 9. So my least common denominator would be 8 times 9, or 72. Now, before we use that, we have to make sure that all the other numbers will also divide into 72. Well, I know that 3 does, because 3 went into 9, and 9 went into 72. I know that 4 must go into 72 because 8 went into 72 and 4 goes into 8. And I know that 6 goes into 72 because 6 divided into 72 is 12. Okay, so 72 is my least common denominator. A larger number would work, however, it's going to give you bigger numbers to work with. So try to find the smallest number that all of your denominators will divide into. So I'm going to take the entire equation times 72, and that means take 72 times all of these terms. So I have to take 72 times every single fraction. Now you can certainly do this on a calculator. I'm going to show you how you can simplify this without a calculator. So on this first problem here, I need to take 72, and I'm going to do a little scratch work over here on the side. I want to take 72 times 2/3. Now the easiest way to do that is to do the division first. Take 3 and divide it into 72. And if you don't know what that is, then you'd have to do a little division off to the side. 3 goes into 7 twice, the remainder of 1. 3 goes into 12 4 times, the remainder of 0. So 3 goes into 72 24 times. So once I do that division, what's left over? 24 times 2. So that means 72 times 2/3 is a 48, and that x stays put. Okay, let's try that again. I'm going to bring down my subtraction, and now I need to do 72 times 3/4. So 72 times 3/4. Do the division first. How many times does 4 go into 72? It goes in 18 times. And again, if you didn't know that, then you'd have to do some little division off to the side. What's left over after you do that division? 18 times 3, which is 54. So 72 times 3/4 is 54. Okay, let's keep going. 3/8 now needs to get multiplied by 72. So I'm going to take 72 times 3/8. Do the division first. 8 goes into 72 9 times. What's left over? 9 times 3 is 27. So 3/8 times 72 is 27. Bring down the minus sign. 1/9 times 72. So 72 times a 9th. Do the division first. 9 goes into 72 8 times. 8 times 1 leaves me with 8. So this will be 8 and an x. And finally, our last one, I'm going to bring down my plus. 1/6 times 72. So 72 times a 6. Do the division first. 6 divided into 72 is 12. You can do that with some scratch work division. What's left over is 12 times 1, or 12. So this will be a 12. So there's quite a bit of scratch work to do on that if you're doing it all by hand, but you can always use a calculator as well if your instructor allows it. Now look at what we are left with. We've cleared out all of our denominators, and we have much nicer numbers to deal with. Before I start moving terms around, I do have a couple like terms on the right-hand side, so let's get those together. So I'll have 48x minus 54 equals 27 plus 12 is going to be 39 minus that 8x. And I am going to want to get these x's together, so let's add 8x to both sides so that these 8x's cancel out. 48 plus 8 is going to be 56x. Bring down the minus 54. Bring down the 39. So we have our x on the left side, so now we need to move the numbers to the right side. So I'm going to add 54 to both sides. So these cancel out, giving me 56x equals 39 plus 54 is 93. Then to finish it off, I need to get rid of that coefficient. So 56 is being multiplied by x, so we have to divide by it to undo it. So x equals 93 divided by 56. And you just want to do a quick check to see, is that fraction reduced? 93 is divisible by 3, but 3 does not go into 56. So it is a reduced fraction, and we're ready to put our box around our final answer. Okay, that was a tough problem that had a lot of work in it, especially if you're doing it all by hand. But if you take it step by step, you can make it more manageable. Let's try another example. Now this one is kind of similar to the last example, but it has a different look to it. When you see a problem like this, one way to make it more manageable and make it easier so that you don't make any mistakes is to realize that there are implied parentheses around this numerator and around this numerator. So write in those parentheses around the x plus 3 and the x minus 3. It will really help you make fewer mistakes. So what I want to do when I first look at this is clear out those fractions. And I'm going to do that with my common denominator. If I have a denominator of 5 and a denominator of 4, my common denominator has to be 20, 5 times 4. So we're going to take both sides of the equation times 20. Now when I do that on the left side, keep in mind that we're doing that division first. So 5 goes into 20 4 times. So look at what would be left over. This 4 and all of that x plus 3 still wrapped in parentheses. Those parentheses are important because if you don't put them in there, then you're not going to remember to distribute that 4 across. Okay? Now what we're going to do is take 20 times this fraction. So if we take 20 times all of this, doing that division first, 4 goes into 20 5 times, what I will be left with is my 5 and my x minus 3 still in parentheses, and there was subtraction between these two terms. So again, these parentheses are really, really important because in the next step, we're going to need to distribute that negative 5 across. If you don't put the parentheses in there, you will forget to do that distributing. On the right side, don't forget to multiply this right side by 20 as well. 1 times 20 is 20. So here's our new equation, no more fractions. Now we do have some parentheses still in the problem, so the next thing we need to do is get rid of those, and I'm going to distribute my 4 across. So I get 4x plus 12. On the next step here, when we distribute, you want to distribute the 5 and the negative. So negative 5 times x is negative 5x. Negative 5 times negative 3, notice there's 2 negatives. An even number of negatives become positive. So negative 5 times negative 3 becomes positive 15. That's probably the number one mistake that I see students make, is forgetting to distribute that negative across. Okay, we've gotten rid of our parentheses. We still have some like terms left on the left-hand side. So let's combine them. 4x minus 5x is negative x. 12 plus 15 is 27. Now we have our x on the left side. Let's get our numbers to the right side. So right now I have addition by 27. I'm going to need to subtract it to undo it. When I cancel this out, don't forget that there's still a negative in front of that x. 20 minus 27 is negative 7. Now we're not quite done. Negative x equals negative 7 isn't completely isolated. The x isn't totally by itself because this negative is like a negative 1 in front. So there's still a coefficient there that we have to undo. So all I have to do to get rid of a negative is divide. Divide both sides by negative 1. We get x by itself, a positive x. And over on the right side, negative 7 divided by negative 1 turns into a positive 7. So our solution is x plus 7. Okay, the next example is very similar to the last one. We have these two fractions, and in order to keep straight the fact that the numerator, the entire numerator, is being divided by the denominator, I would recommend putting in those parentheses around the two numerators, just like this. And the first thing we want to do to solve this equation is try to clear out those fractions which are causing us some trouble. So if we look at our two denominators, we have a 3 and a 6. That means our common denominator should be 6. So I'm going to multiply the entire equation by 6, the left, the middle, and the right. And when we do that, on this first fraction, remember, divide the denominator into that 6 first. So 3 goes into 6 twice. And that means we're going to have a factor of 2 left over times that entire numerator, 2m minus 3. When we go to the second fraction, this time the 6 cancels out that 6 completely, so we only have the numerator left over. Now, if you wanted to, you could put a 1 in front of those parentheses, but notice you do need to have the parentheses, and that's because we need to distribute this negative across to the 4m as well as to the negative 2. That's probably the number one biggest mistake on this problem, is forgetting to distribute that negative. So reinforcing those parentheses and keeping them in there is really going to help you avoid that mistake. Now don't forget to multiply by the 6 on the right side as well. This time nothing cancels out because we don't have a fraction and we don't have a denominator. So 3 times 6 would be 18. Now we have no more fractions, but we do have parentheses, so we want to clear out our parentheses by distributing. So 2 times 2m is 4m. 2 times minus 3 is minus 6. Minus times 4m is minus 4m. And minus times negative 2 becomes positive 2 equals 18. Now on the left-hand side, we do have some like terms. Notice that something kind of weird happens on this example. We have a 4m and a minus 4m, so those two terms actually end up canceling each other out. You don't need to write 0m, they just become 0. So they totally disappear. That means the only thing we have left is negative 6 and a positive 2, which is negative 4. Now be careful, whenever your variable disappears like it did on this example, it's always very important that you look to see what is left over, because what's left is either going to be a true statement or a false statement, and which case it is will determine what your final solution is going to be. So in this problem we were left with a negative 4 equals to an 18, which is obviously false, and that's a conclusion, but it's not our final answer. If we have a false statement like this, that means that no matter what I were to plug in for m, no way would this be possible. I'd always end up with a false statement no matter what I chose for m. So what do you think that means that m needs to be? If nothing ever works, and it's always going to end up being false, then there must be no solution. So your final answer should be no solution, or you can put 0 with a slash through it, either way. Okay, so just be careful on these problems with the fractions. Multiply through by a common denominator, but make sure that you use parentheses around those numerators and distribute carefully. Okay, on the next example, we're going to talk about how to clear out decimals. So if you look at this example here, all of these have decimals. Now, if you have a calculator, you could certainly use your calculator to help you out on this. It kind of depends on your instructor and whether or not they allow calculators. I'm going to show you how to do it completely without a calculator. So if I wanted to get rid of these decimals, what we're going to need to do is multiply by an appropriate power of 10 so that those decimals will all disappear. And the key to figuring out what you should multiply by is counting how many digits come after the decimal. So for example, 0.4 has 1 digit, 2.7 has 1 digit to the right, 1.6 has 1 digit, 4.6 has 1 digit, and 2.7 has 1 digit. So they all have one decimal place present. So if we want to get rid of that decimal place, what we can do is multiply by 1 power of 10. You want to use the power of 10 with the correct number of zeros as however many decimal places you see present. So since these all have exactly 1 decimal place, I'm going to use exactly 1 0 and multiply every single term by 10, like this. Now if you had terms that had more than 1 decimal place, maybe you had a 0.4 and then maybe you had a 2.75, then you'd want to multiply by the largest number of decimal places you have. So if you have one term with 1 decimal place and another term with 2, then you're going to want to make sure you clear out all the decimals, so multiply by the bigger number. So I'd multiply by 2 powers of 10, which would be 100. You want to use as many zeros as decimal places. Now when you multiply by tens, the reason why this works is because multiplying by 10 just shifts that decimal one position to the right. So when I do 10 times 0.4, this decimal moves one spot to the right, and we're left with that negative, and now we have 4x, no more decimal. When I multiply 10 times 2.7, the decimal moves one spot to the right, and now I'm left with 27. When I multiply this term by 10, one decimal to the right, this becomes negative 16x. One decimal to the right, this term becomes negative 46x. And one decimal to the right, this becomes 27. So the nice thing about this technique is it clears out those decimals completely, and now you don't have to worry about them anymore. On the left side, we do have some like terms. So a negative 4x and a negative 16x, they're both negative, so we're really adding, and that gives me negative 20x plus 27 equals negative 46x plus 27. It's all cleaned up, but I do have x's on both sides. So let's get the x's together. I'm going to add 46x to both sides to try and get my x terms together. 46 minus 20 is 26x. Still have my plus 27 on the left and my plus 27 on the right. So now I have my x's together. Let's get our numbers together, and I'm going to do that by subtracting 27 to both sides. That makes this 0 out and this 0 out, so we're left with 26x equals to 0. Now sometimes this is confusing to students, so just be careful here. Finish the problem off. You're not done until you have that x completely solved for. So since this is 26 times x, to get rid of that multiplication by the 26, we just want to divide by 26. And then if you take 0 and you divide it by any number, you're still going to end up with 0. So 0 divided by 26 stays 0. So our final answer is 0. Okay. All right. Another example with some decimals. Now on this one, this is kind of a tricky problem because not only do we have decimals, we also have parentheses to deal with. You have two options here. You could distribute across first if you choose and then deal with the decimals, or you can clear out the decimals first and then distribute and clear out the parentheses. Totally doesn't matter how you do it. Okay, I'm going to show you doing it by dealing with the decimals first and then distributing later. So let's figure out what we need to multiply by to clear out all of my decimals. And you figure that out by counting your decimal places. This first decimal here has 2 digits. This decimal has 2 digits, but this decimal has 3 decimal places, 3 digits. So when you're deciding what to multiply by, you are going to need the amount of zeros that corresponds to the largest number of decimal places that you see. So in this case I have 2, 2, and 3. 3 is the biggest, so I'm going to need 3 zeros. So I'm going to take this entire equation and multiply it by the power of 10 that has 3 zeros, in other words 1,000. So we're going to have to multiply both sides by 1,000. Okay, so now when we do that multiplication by 1,000, this can sometimes be a little bit confusing to students. We're going to take 1,000 times this entire term. This is a term because it's to the left side of that plus sign. Now when I do it times that entire term, we're actually only going to be multiplying it by the coefficient out front. The 5,000 that's still in those parentheses is going to remain unchanged. One common mistake that I see is students will take this 0.02 times 1,000, but then they'll also multiply the 5,000 times 1,000. And that would be incorrect because then you're multiplying by 1,000 times 1,000 or 1,000,000. You're multiplying by too big of a number. So the key to remember here is just multiply the number in front by 1,000. So let's see what that does. When you multiply 0.02 by 1,000, there's 3 zeros, so that means we're going to move the decimal 3 spots to the right. Now 2 spots to the right gets me past that 2. Since I need to go 3 spots, I'm going to have to fill in that empty spot with a 0, so we end up with a 20. This first 0 doesn't need to be written when it's in front of our 2. So 1000 times 0.02 becomes 20, and the stuff in parentheses stays unchanged. Okay? Let's try that again. We're going to bring down our plus, and now we're going to multiply this term by 1000. The p stays unchanged, just like our 5000 did, and we're only going to multiply the coefficient out front by 1000. So I move the decimal 3 spots to the right, past the 0, past the 3, and one more place over, so we have to add a 0, so this becomes a 30. Okay? One more time. On this last term here, this is all one term. So the stuff in parentheses, you just want to immediately recopy it unchanged and only multiply the 1000 times the coefficient out front. So I'm going to move the decimal 3 to the right, past the 0, past the 2, past the 5, so we end up with a 25. So if you look at our new equation here, the stuff in the parentheses hasn't changed. We only changed the coefficients out front, and all the decimals are now gone. Now we want to eliminate those parentheses, so we're going to do some multiplication. Now use significant digits here to make this easier. If I want to do 20 times 5,000, just do 2 times 5, which we know is 10, and then count how many zeros you still need. I need 1, 2, 3, 4 more zeros. So 1, 2, 3, 4 more zeros. So 20 times 5,000 is really 100,000. Okay, now we go to our 30p. Going on to the right side, 25 times 5 is 125, and then I have 1, 2, 3 more zeros. So we get 125,000. And then 25 times p is 25p. So no more decimals, no more parentheses, there's no like terms, so we're ready to get our p terms together. So I'm going to subtract 25p to the left side. That's going to leave me with this 100,000 plus 5p equals 125,000. These zero out. The p's on the left side, so the number needs to go to the right side, so let's subtract 100,000 over to the right side. These zero out, leaving me 5p, and 125,000 minus 100,000 is 25,000. And to finish it off, we want to get rid of that coefficient in front of the p, so if I divide both sides by 5, 5 goes into 25 5 times, and there's still 1, 2, 3 zeros left. So our solution is p equals 5,000. Okay, that was a tough one. Alright, our last example for today has a mixture of parentheses and fractions. So we're going to do one last example on fractions. Now on this example, you have two choices. You can clear out all of your fractions first by multiplying by a common denominator, or you can distribute first to get rid of parentheses and then deal with the fractions. In the last example, we had the same dilemma, getting rid of decimals first or getting rid of parentheses first. And we got rid of the decimals first in the last example. So on this one, I'm going to show you the other way. I'm going to get rid of parentheses first. So let's distribute first, and then we'll worry about our fractions. So this negative 6q stays put, and I'm going to distribute my negative across. So this becomes minus q plus 1/2. And on the right side, 1/4 times q just stays 1/4 q, and 1/4 times 1 becomes 1/4. So now I don't have any more parentheses to deal with, but I still have fractions. So let's look at our denominators. I have a 6, a 2, and a 4. I need a number that all of those will divide into easily, and I want it to be the smallest number that will work. Well, 2 times 6 is 12, and 4 goes into 12 as well. So I'm going to use 12 as my least common denominator and multiply all of my terms by 12. So this times 12, this times 12, this times 12, this times 12, and this times 12. Okay? So over here we need 12 times negative 5, 6 cubed. Let's do a little scratch work for that. So 12 times negative 5/6. Remember to do the division first. 6 divides into 12 2 times, then you're just going to multiply what's left over. 2 times negative 5 is negative 10. So this is going to be a negative 10 and a q. Now we're going to do 12 times our minus q. There's no fraction there to cancel anything out, so we just have a minus, our 12, and our q. Then we bring down our plus. Now we want to do 12 times a half. That you could probably do in your head. Half of 12 is 6. Okay? Over here, we're going to do the same thing. 1/4 q times 12. If you need to do scratch work, do the division first. 4 goes into 12 3 times. 3 times 1 leaves me with a 3. So 1/4 q times 12 is 3q. And then for the last one, 1/4 times 12, that was that 3 again, but this time there's no q. So we've cleared out our parentheses, we've cleared out our fractions. We do have a couple like terms over here on the left side. Negative 10q minus 12q is negative 22q. Now I want to get my q terms together. I'm going to add 22q to the right-hand side. So I have 6 equals 25q plus 3. Q's on the right, so numbers need to go to the left. So let's subtract 3. 6 minus 3 is 3. So now to finish solving for q, I have to divide through by that coefficient. So I'm going to divide both sides by 25. And I get q equals 3/25. That's a reduced fraction, so I have my final answer. Alright, that concludes our lecture on solving linear equations. Good luck.